that we are out of this situation, this very nasty situation, quick enough, and we can have a full lecture room again. Okay, we're going to continue with the material on space. I have loads of material to share with you, so sorry for giving you quite a bit of information today. As said last week, the idea of this course is not only to give you information on the contents of spaceflight, so you can make a first-order design of a vehicle or a mission or whatever, but also to share with you what is ongoing in spaceflight as we speak. News of the day. I would like to do it once per week, but I was forced, of course, to share it with you what happened this week, today already. No question about it. The highlights, if you want to, the lowest point of this week, maybe even of the entire year, a completely insane experiment by the Russians. Completely insane. Did they do a test like that? Maybe from a certain perspective it is understandable, but then don't try it on the spacecraft. It was one of their own, of course, we can be happy with that. A spacecraft that is flying at an altitude of about 480 kilometers. What you find at that altitude is the International Space Station, the Chinese Space Station, plenty of operational spacecraft from whatever nationality. All of that is put at risk because of this particular anti-satellite test. You see it here. It created what we can track at this moment, 1,500 what's called larger pieces of debris. We'll take a look at the debris problem in a few weeks from now. But that can be tracked. But expectation is that there are hundreds of thousands of other parts which are just as lethal for the space station, for anything that we might have, just as lethal. And they go about completely uncontrolled, unpredictable, whatever. So really it was creating a very nasty situation, still is, and a lot of anger with many, many people. Debris field is set at this particular altitude, and that's exactly where you find the Chinese station, but also the International Space Station, with US astronauts on board, European astronauts on board, also Russian cosmonauts. So in a way, they expose danger to their own countrymen. It's a completely insane exercise, absolutely. I took the liberty of also spending a next sheet on this, the reaction from the top guy from NASA, the administrator, Bill Nelson. And he said, earlier today, the thing happened due to the debris generated. We had to take special measures for the safety of the people on board of the space station. I am outraged, and that's a very nice way of putting it. I am outraged by this irresponsible and destabilizing action. It really, I'm also putting it mildly, it is not making friends. This is the most silly experiment that you can do in space, absolutely. Actions are reckless and dangerous, threatening as well the Chinese space station and the taikonauts on board. All nations have responsibility to prevent the purposeful creation of space debris from ASATs and to foster a safe, sustainable space environment. The number one problem that we have in spaceflight is space debris. And those crazy guys who push the button, they're only making it much and much worse. The space station, International Space Station, is at a certain risk when it comes to space debris. I read it somewhere on one of the websites. The current risk for the space station has been multiplied by a factor 4. That is a very major issue, a very major concern. It's absolutely crazy thing. The crew on board the space station was awakened and directed to close the hatches to the radial modules. So the space station has all sorts of, you cannot see it clearly here, but it has all sorts of protrusions, all sorts of cabins and modules sticking out to the left and to the right and up and down, I don't know what. They had to close the hatches in case one of those modules is being hit by a space debris particle, then only that particular module is affected and not everything else. This really was an utmost emergency situation, absolutely. The crew, you can read it for yourself, they had to go to the lifeboats, Soyuz capsules, so in order there would be a major impact, they could push the button and go safely down to Earth immediately. It was that threatening. And a situation like that pertained for a couple of hours, And in a way, it's going to repeat regularly. Did any one of you, let me see some hands, did you see the movie Gravity? I saw it as well, of course, a completely crazy movie. Many technical aspects were absolutely wrong. But the first 15 minutes of that movie, where you see the debris coming in and impacting and whatever, let's be honest, that was frightening, right? That is the situation that we are confronting since last Monday. A completely crazy exercise. Absolutely. Well, enough about that. We could continue for another hour. That's not the idea of this lecture, but it is a serious thing. Let's be optimistic. Under the assumption that the space station is still alive in the coming week, I happened to run into it at the NASA website. They did make predictions when you can see it here from Delft. You can type in any name of a city anywhere on the surface of Earth, and get a prediction of when the space station is visible. You could see here when it is appearing, when it is going below the horizon. You can also see that's maybe a very good aspect. The maximum height, the maximum one goes here to an elevation of 63 degrees above the horizon. So that might be your preferential slot to take a try at least. Of course, the real risk factor in all of this is weather. If it is cloudy, it's a no-go. That's clear. But take out your simple binoculars. I have done it a number of times. Try to pick up the space station, and it is very, very impressive to see it live going about Earth. So there's plenty of options in the coming week and also the week after. Feel free to check the NASA website and fill in your own time slot and coordinates. Also related to the space station, another interesting thing and very, very representative of what we're doing at this very moment, that is the departure, that is leaving the space station, a certain module, the so-called Cygnus model, SWAN in English, that has been docked to the space station for something like 3 months in a row. What is special about this? This is a very nice example of what we call new space. It will be on the table in this first lecture hour as well. It is the 16th commercial resupply mission to the space station. We used to do it old-fashioned style with a space shuttle. Of course, that came to a halt about 10 years ago. At this moment, we have Russian launchers taking people up and down, but we also have, as we speak, the opportunity to use new programs, commercial programs, to serve as a taxi, as a cab, and take people to and from the space station. So this is just one of the very clear, exposures of this concept of new space. Okay, enough about news of the day. Feel free to check out the NASA website and the ESA website and whatever you can find, and keep up to date with what is ongoing. I'm going back to contents of the lecture, and I would like to share first of all with you some historic considerations, and then see where we are at this very moment. Going into history, let's first take a look at who, so to say, the main players have been through the ages. I hope I'm not offending anyone here in the audience, but the first name on the list here, Copernicus, goes back to 1543. He was in a special situation. He was in the situation when society was governed by the Catholic Church. And again, no offense, but the ideas that were, so to say, forced upon us was that, first of all, Earth is central. The Earth is the central object in the universe, whatever that is. And secondly, spheres, circles, I should say, are the ideal geometric shape. Copernicus, he thought about it very critically, and he came to the conclusion, no, it cannot be for a particular reason. It cannot be that Earth is central. The sun should be the central body, or is the central body in our universe, at least in our solar system. That was, of course, one-on-one against the current ideas or the ideas of the Catholic Church. So he did not dare to bring his ideas out into the open until his very last year being alive. Absolutely, that was a very dangerous thing to say. But he turned out to be right. The sun, indeed, is the center of our solar system. The next name in the list, also a famous name, we'll encounter that guy also repeatedly, Johannes Kepler. He took it one step further. He had observations, not done by him, but by one of the fellow astronomers way back then. Does anyone know the name of the guy who provided input to Johannes Kepler? It was a guy from Denmark. Tycho Brahe, exactly, a guy from Denmark. He was the observer. He took accurate observations with a telescope and noted down when and where Mars or any other planet could be seen. Johannes Kepler was the guy who said, well, that's an interesting problem. What would that represent? Where does it come from? Can I make anything meaningful out of that? And he did indeed. He came up with his observations saying that the planets, indeed, confirming Copernicus, go about the sun, and they go about the sun not so much in circles, the holy shape until that moment, but in ellipses. And he also said something about the time it takes to complete one revolution. We're going to take a look at that tomorrow, so let's not go into too much details. But again, that was revolutionary when that was put on the table, absolutely. There's one thing though, it is what we called empirical laws of observation. He had no explanation for this. He just saw what was happening and sort of made a connection between the points and said, well, then the shape has to be elliptical and so on. But he had no clue what was causing this particular motion. For that, we had to wait another century, so to say, when Isaac Newton came around. You all know him from the famous experiment, true or not, with the apple falling from the tree. He said, well, there is this aspect, gravity, and actually gravity, or the way in which it can be modeled nowadays, or then gravity gave the explanation to what is ongoing in our solar system, the dynamical explanation what is ongoing. Those two guys, and if you want to, feel free to also include Copernicus, they really are the heroes when it comes to classical celestial mechanics, absolutely. Thanks to them, we understand very well what is ongoing at this moment, and with a very, very high degree of reliability. Kepler orbits, again, we'll have them on the table tomorrow. They are correct for something like 99.99% of what is really happening. So, dear Mr. Johannes Kepler, dear Mr. Tycho Brahe as well, dear Copernicus, dear Sir Isaac Newton, thanks for doing all of that. Okay, Jules Verne, he was a science fiction writer. You might have read his book, I don't know, otherwise it's nice to do so. Konstantin Tsiolkovsky, a school teacher from somewhere in Russia. He came up with a nice treatment on the motion of rockets. We also have that in more detail on the table in like 2 weeks from now. He also was one of the pioneers when it comes to space flights. And then in Germany, we had Hermann Oberth and Walter Hohmann also coming up with certain ideas about space flights. We also will have a look at those persons later on. A number of very famous persons when it comes to the history of space flights. That is all about theoretical ideas, about paperwork and so on and so on. When it comes to designing real, not so much missions yet, but real vehicles that can be taken into space. There are some other names that can be brought to the table. First of all, you see him here on the left. We have Robert Goddard doing the first experiments with liquid launch vehicles. It's maybe a bit difficult to recognize, but we have here on the top part, we have the rocket itself, and that's connected to something down here, and that contains the propellants. So the thing apparently is ignited and hopefully successfully lifting into the sky. And by doing so, just experimenting, hardly knowing what to do, Robert Goddard and his colleagues, they were able to develop the technology of spaceflight, of rocketry. In Russia, there was a similar guy, famous guy, I should have his name in red as well, Sergei Korolev. He's one of the persons included in this particular picture, and they also developed their, say, Russian counterpart of the liquid rockets. And of course, then a famous, depending on your ideas, maybe notorious, but for me at least, a famous person is Wernher von Braun, of course. He started his career, if I might call it like that, in Nazi Germany with the development of the notorious, we agree about that one, the notorious V2. Yes, and that was, say, the foundation of the modern rockets as we have it at this moment. And they were developed further and led to the so-called intercontinental missiles that can travel from, say, either the US to Russia or from Russia back to the US or whatever. So very soon it was turned into a weaponry system that is maybe not so good, but this is what happened. When it comes to vehicles, when it comes to spacecraft that we have in object, the very first one, of course, the famous one is Sputnik 1. We're speaking about October 1957, the launch of Sputnik 1. I will have a very brief movie to share with you in a moment that really shook the world. Everybody was extremely excited, if not nervous, if not panic-stricken about this, but that really started everything in space itself. The Americans, of course, they could not stay behind. They did not want to stay behind. So very soon, it was a crash effort, absolutely, but very soon they came up with their first satellite, Explorer 1, and that was launched at the beginning of 1958, just a few months later. Already in 1959, that is a year and a half after the Sputnik, the Russians had another great achievement. They managed to have a vehicle taken to the moon. Not successful in the sense it's going to orbit around the moon, but it was successful in reaching the moon and doing a, hard landing, if you want to, crash landing, but still being able to reach the moon. So a very, very good achievement. Only a year and a half after the very first launch. Really very impressive. The Russians, again, they were the first when it came to manned spaceflight. Yuri Gagarin, famous cosmonaut. He was the very, very first one to be in space and go about in what we call a sustained flight, not just hopping to 100 kilometers and then back down to Earth again, but really be in orbit for by heart, something like a day. So again, a great, great achievement by the Russians. Here as well, the US counterpart, they could not stay behind. John Glenn was the first US astronaut to be in a sustained flight. He was not the first one to go above 100 kilometers, but again, the first one to be in a number of successive revolutions. Let's go back to Sputnik 1. You see a picture here. It's a very small sphere. It measures like, slightly more than 1 meter across. A very modest mass, only 80 kilograms, and it was emitting signals to the Earth, and again, was quite a successful experiment, absolutely. Now, let's see whether this goes okay. Okay, guys, we have an issue with sound. No idea what goes wrong, but I'll try to do the voiceover here. This clearly is the launch of Sputnik 1. You see it here in orbit around Earth. The Russians, of course, are extremely happy with this. You can imagine that. Khrushchev, the head of Russia way back then. This is not the real thing. You understood that. Gagarin standing here on the right, and this is President Kennedy making a statement. We will be the first to be on the moon, at the start of the famous moon race, and we will beat the Russians and make sure that we are doing perfectly okay. And that was the destination then, the moon, of course, with, the space race, the moon race, which had the Americans in the end as the winners. Sorry for all the hassle. Where are we? Yeah, okay. Okay, you saw the movie, you saw the satellite, at least in animation, going about Earth, and that, of course, was a great achievement by the Russians. In real life, the satellite was giving bleeps of radio waves, bleep, 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 bleep. That was the real situation, the physical situation. The perception of the audience, and certainly the ones in the US and maybe also in Western Europe, was the satellite was overflying and it said, I control the world, I control the world, I control the world, I control the world. That was exactly the fear that was coming out of this. The Russians have something put in space. They can overfly any territory on Earth, and they can do from that position whatever they would like to do. Whether it is just observations, but maybe also dropping a bomb or whatever. Really, the Western world was panic-stricken by this. And the only consequence that came out is that the Americans said, we have to start on something similar. We have to develop our own space machineries, and we will make sure that we are certainly not beaten by our dear friends, the Russians, right? So that sort of triggered the space race. Okay, satellites or events. Venus, I told you about reaching the moon already a year and a half after the first one. In 1962 already, the very first US vehicle was able to reach Venus. And again, do not think about it lightly. Venus is a planet which is there, far, far away. It looks like this if you study it with a telescope or what. So aiming your spacecraft in that direction and being able to end up there. I don't know whether this was another crash landing or whatever, but it was a great, great achievement, absolutely. 1965, that saw the first what we call spacewalk, an extravehicular activity, an activity outside of the vehicle. That was, again, a Russian, Leonov. And in 1967, we had the first launch of the biggest vehicle, the biggest launch vehicle ever, Saturn V. Have you guys ever had the opportunity to go to Kennedy Space Center? What did you see there?
Yes, they have this rocket lying on the floor there.
And what did, yeah, really impressive indeed. You're standing there and it is like, ah, wow. It measures like, sorry, say again? The engines are crazy, absolutely. It measures something like 110 meters in length, in height. Well, it's sort of taken apart in the different stages, but it is extremely impressive. If you ever get a chance to go to the US, do not forget to go by in Florida and visit Kennedy Space Center, absolutely. 1969, a famous year with some famous people. Of course, Neil Armstrong, the very first person to land on the moon, or to step physically on the moon, and he was accompanied by Buzz Aldrin. There was a sort of poor third astronaut. He had to stay in the vehicle that was going about the moon still. But he had to wait for one day before Aldrin and Armstrong were taken back to the mothership and then taken back to Earth. But this was a famous date, absolutely, the first steps on the moon. And in 1976, we had the first landing on Mars with the famous Viking vehicles. Very, very impressive indeed. Holland or Europe could not stay behind. ESRO, the first European satellite, was launched in 1968. Again, within a decade or slightly more than a decade after the first vehicle ever in space. And also Holland had its first vehicle in 1974, the famous ANS thing. Sorry, I have some more to share. I'm going to skip this one. I just want to share with you one remark, important remark that is made in this particular movie. It's done in a comment made by the Apollo 12 astronaut Bean. And he said, very rightly, we had no books. We had to learn everything from scratch. We had to invent everything. We had no idea how things worked, no idea, but we simply were eager enough to keep up with the Russians. We were extremely motivated to develop all sorts of things, and we simply did it by experimenting, by working hard, by working late hour shifts and whatever we have. No books. If I'm very, very black and white, we, you, but also me, we are in a very lucky situation because we do have books, we have textbooks, we can learn about orbital mechanics, about the principles of rocketry, about attitude control, about operations and so on. Those guys, they really were the pioneers. They had to invent everything from scratch. There was absolutely nothing there. If you take a look at how JPL, the Jet Propulsion Laboratory in the US, how that came about, they literally started in the desert with nothing, absolutely nothing. So kudos to those guys, absolutely, absolutely. Important days and events, very quickly. One highlight certainly is the launch of the Voyager 1 and Voyager 2. That took place in August and September 1977. There is one person here in the audience who was the witness of that, not physically, but at least he was here in Delft already. Very similar to you as you are at this moment. I was starting my study aerospace engineering in September 77. That happened, and at least the ones in our batch of 125 who were excited about spaceflight, we were like this, whoa, what is happening here, and what a great thing that can be achieved. The idea about Voyager is very special. It did what is called the Grand Tour. It started out at Earth and then had a number of flybys around Jupiter, around Saturn, and then on to the next two planets, and finally going off in the darkness of space. At this moment, both Voyager 1 and Voyager 2, they're still active. At a huge distance, something like 120 or 140 astronomical units, but they still operate, they still send a little bits, tiny bits of information to Earth, and they're still doing a great job. By the way, they also have what is called the golden records on board. For some reason, people said, well, if there is any civilization out there, we would like to share with them that we are also a certain civilization and the kind of things that are representative for us. So way back then, it was put on a very, very fancy, modern piece of technology, an LP, long player. You probably do not even know about it. I still have my old LPs. I still play them, old-fashioned music, doesn't matter. It was put on those two vehicles with the idea, okay, if someone picks it up, they can see where we come from, and so on and so on. There were also people who said, don't do that, because you're only giving away the location where we can be found, and they will come to us, and not only come to us, but have us for a snack or whatever. So there was quite a serious debate about all of that. Okay, the Ariane, European launcher, first flew in 1979. In 1981, very important highlight, the first flight of the Space Shuttle Transportation System, the very first flight. It has been up and running for quite some time. I will tell you some more about it in the next hour. After that, 1990, we saw the launch of the Hubble Space Telescope. In my personal opinion, the most valuable, the most precious vehicle that has ever been launched and operated. It is still ongoing at this very moment, so that's more than 30 years after the launch. And also at the end of the previous century, we saw the launch of the first elements of the International Space Station. Okay, that was your history. Where are we at this moment? What is ongoing right now? Well, quite a lot, and to be honest with you, extremely exciting, extremely successful. Last week I already shared with you the general outcome of the 1990s. We tried a lot, but everything failed. But now, in the 21st century, there are a great number of developments, and almost all of them with great success. And the most important one, of course, the most remarkable, is what we call new space. We are not doing it old space style, but we have new space. And what is new space? The most important element, there's a prime role for individual commercial companies. In the old days, we used to rely only on the big organizations, like NASA, like ESA, like the Russians, Roscosmos, whatever you have. They would provide money, they would tell you what you can do and what you cannot do, And if you're lucky, you could fly your own experiment or maybe develop your own spacecraft, but that was about it. At this moment, we are not taking no as an answer anymore. Companies simply say, well, who cares? I have plenty of money. I will start my own mission and I will see where it ends. And it holds for the big guys. The names will be coming up in a moment. But it also holds for students. ISIS, or ISIS Space as it's called nowadays, started out with five students who graduated on a certain satellite project here in-house. And they said, well, we can always work at Airbus or whatever, but we prefer to have our own company and continue working on this. So they started with 5, very nice situation, 5 directors, okay? But at this moment they have like 80 or 90 people working with them, and they are great. They are selling all over the globe. It's a great commercial success, absolutely. They're not taking no for an answer. They simply did it and were successful. So, developments driven by private funding, commercial entities. NASA, do you want to take part? Be my guest, pay a price, but we do not really need you. Reduction of cost, that is the idea. NASA, ESA, they've always been focused on quality. No matter what it costs, quality, quality, quality. And reliability and whatever you have, but all on technical stuff. New space starts with a different agenda. It starts with recognizing the fact that at the end of the day, a bill has to be paid. So if that is attractive, if the amount of money involved in a project is not too high, you will be successful. And we will prove it. They did prove it, absolutely. So we have SpaceX, of course, with the Falcon 9 and the Falcon 9 Heavy, and the capsule taken cargo or persons to the space station. And now also for tourism. We have Northrop Grumman, same story with the Cygnus capsule and their Antares launcher. We even have an old player like Boeing. Boeing is involved in spaceflight already for 50, 60 years. But I said, well, the scenery is changing, we have to adapt. If you continue business as usual, we might be blown out of the water at the moment, so we also have to introduce new projects in a new way, and they did so. So when it comes to flying to the space station, they simply offer a service. NASA, would you like to take astronauts to the space station and back? What do you say? 2 times per year, 3 times per year? Would you like to have cargo taken to the space station? We can do it for you. We have this cap. All you need to do is step in and pay the fee for going up there and be taken down again. That's the way it is done at this business, at this time. Completely different business model than what we had before that. Reusability of rocket stages, same story here. Unthinkable 20, 30 years ago, but now we do it. And now let's see where the movie can start again. Keep your fingers crossed. Keep your fingers crossed. Maybe I should already start yelling, "Dear TA, please come." To the mark, right? Yeah. Okay, this is a SpaceX landing. And sorry again, the noise disappeared. It is on my laptop. But when you look at the YouTube movie, you hear the people screaming and yelling and I don't know what, because this was one of the very first successful landings of a booster on what is the ship, a barge in the Pacific, and clearly this is something that can be used again. It is available in the presentation, so feel free to play it again at your own time. It was a great achievement. I hear the people yelling here, but that's not helping you that much. Sorry for that. Okay, let's go back to full screen. Yep. Okay, so reusability. You see it also here in the picture on the lower right. Reusability for the booster landings. You can see that the far majority shows color blue. It is drone ship success. It is landing on the ship, can also land on land, but it is used again, so that's a nice way, a very nice way to reduce the cost of putting things in space. Okay, space tourism, very briefly. We have a very exciting year, 2021, because we had a flight of the Spaceship Two vehicle with 4 passengers on board. The New Shepard by Blue Origin in July of this year, also with 4 passengers. And the Crew Dragon by SpaceX with 4 passengers going to an orbital situation. Unthinkable space tourism, but people simply do it nowadays. They get permission from the FAA, that's safe, and if there are any paying customers, then certainly it can be done, and we will do it. Very briefly, we have arguments about what is spaceflight. You can see the altitude regimes in the plot up here. You might recognize the line here. It says Kármán line, 100 kilometers. And you can see that Spaceship Two and New Shepard, Spaceship Two went to about 90 kilometers. New Shepard went just above 100 kilometers. Depending on your definition, it is not yet sustained spaceflight. So people say, well, okay, you reach a certain altitude, but then you fall back, it's all ballistic, and you have been in space, but you're not an astronaut yet. So there's a bit of a debate about it. What do we also have nowadays happening in spaceflight? First of all, there is this appetite for this appetite for larger satellites. That's what you see here, in particular for geostationary applications, with our hunger for more data coming our way, real time, high quality data. But also we have, of course, the smaller satellites, because we want to reduce the costs, because we want to reduce the risk for any vehicle, rather than a big satellite. If it is hit by a space debris object and the entire mission is lost, we like to smear it out over a number of smaller spacecraft. If then only one is hit, you still have the counterparts that can continue the mission, or the largest part of the mission, that's for sure. We have the development of constellations. There's quite a bit to say about that. OneWeb, for instance, and SpaceX also, with constellations that might even go up to 30,000 elements. Non-classical players, like you and me, universities. It was impossible for us to think about contributing to a real mission. Maybe with one instrument, that's it, but not having a complete spacecraft. Well, with CubeSats, we, and again, we can actually do that. What nicer than to build your own CubeSat in a team with other students and have it flying at a certain moment and operating for many, many years. Launchers, reduction of cost. We develop launchers, small launchers. We also develop bigger launchers for a very simple reason. We are ambitious in our targets. We want to go to Mars with a crew of 4 or 6. So you need bigger vehicles to be able to take you there. And finally, also what we call hosted payloads. You do not necessarily have to design your own new satellite for any new mission. Maybe it's good enough if you simply have your instruments and have to take on board another vehicle. Can be a much, much cheaper way to do business. As a consequence, there is quite a bit of competition between the classical solution for communication, that is using satellites in the geostationary belt, versus what we have when it comes to constellations. There are pros and cons, and believe me, there is a very serious battle ongoing between operators, whether you go for the traditional one or for the alternative. Constellations, 2017, we had the first launches of vehicles from the Globalstar constellation. In 2018, another set, 2019, there's a long list going all the way to 2029. And in the end, the expectation is that we will end up with about 100,000 spacecrafts. Good or bad, you can have your own ideas about this. I think we all recognize the concern, at least the concern, that it will contribute quite a bit to the space debris problem. So instead of having this in 2017, we are going into this situation, and the very fundamental question, is this acceptable, yes or no? CubeSats, the small blocks, 10 by 10 by 10. You can fly them by yourself. You can also stack them with 3 or 6 or 12. The most important thing is that they're very lightweight and very cheap. fabrication and launch and so on. It's not necessarily a solution to everything, but it is something that can be done. Some examples, Delphi C3, Delphi Next, developed by your very predecessors, absolutely. Lumio, a mission to the backside of the moon. We, people from Delft, people from this very faculty, even I myself, we are also involved in this project. And then, for instance, Planet Labs, they have their Dove concept, a 3-unit CubeSat, and it has been flying already for quite some time by now. Let's not take a look at everything here. I just want to emphasize here that you could ask the question, are they reliable, yes or no? Well, initially, when they started in 2002, they were not so reliable, but now we have stabilized at something like 70 or 80%. So that is very, very impressive for the things developed by students and so on and so on. So we're learning quite a bit here. I want to complete the current trends, and then we have a break, no worries. I know that the clock is ticking. Other trends, manned missions to the moon and to Mars. Again, international competition. It's not only the NASA's and so on are doing it. We also have private companies doing it, like SpaceX. NASA and ESA, they have their gateway concept for this particular purpose. Larger rockets are on the table. The idea is also to use materials that can be found in place, in source, or in situ, resource utilization, and also 3D printing. 3D printing will play a role here. There's a role for low thrust propulsion here, because of efficiency reasons, in particular for interplanetary missions. Solar sailing sounds like a very exotic sci-fi kind of thing. We have been testing that for already quite some time, and it is at the doorstep, so to say, of becoming truly operational. I have one colleague upstairs, Jeanette Heiligers, and she's working on solar sailing full-time, a very, very nice technique indeed. Green propellants, we don't want to contribute to pollution of the atmosphere or whatever more than needed, so that is something that is in development. Think of even water as a propulsion thing that is considered at this moment. Development of space stations, robotic missions, increase of data rates, laser links, and so on and so on. Back to private companies going to I don't know where. I'm a very how do you call it? I like very much to read the monthly Donald Duck magazine, not the weekly, but the monthly one. And I was very pleased in 2016 when I saw this cover of one of the versions, one of the booklets way back then. It says milliardaire, billionaire on Mars, and clearly it is inspired by the plans of Elon Musk, of course. He is the rich uncle, like, what is it, Uncle Scrooge? The rich uncle who can say, okay, I have deep pockets, I am prepared to invest money into that, and yeah, let's go to Mars or whatever. You can have your thoughts about that, but there's also a very serious element to this, and that's certainly something that I would like to share with you. That is the person that we see sitting here at the back, Willy Wortel. What's his name? Footloose something? Willy Wortel, the inventor. My dear friends, that's you. You could really contribute to whatever development we have on the table at this moment and be part of the future of spaceflight 5 years, 7 years, 10 years from now. One of my former students, he works at SpaceX, he comes back with great stories. It really is something that could be your future if you're ambitious enough, something very, very nice for you in that. When I was a student, as said a long time ago, we had a hero, an absolute hero. Carl Sagan. Do you know his name? Anyone heard of Carl Sagan? He was, what was he by profession? Communicator. Well, he used to present on television and so on. He was an astronomer by profession. And he would comment about the missions, the Voyager missions and so on and so on. And we were all dying for the guy, reading his books, following his documentaries on the television and so on and so on. Now, 50 years later, 45 years later, I'm more than open to say that at least I, and I hope for you as well, I have new heroes. And here they are, of course. Jeff Bezos saying there are no laws of physics against this. That is, against the further development of rockets. If you understand the laws of nature, you can apply them in a smart way and reduce cost. Of course, Elon Musk, when it comes to traveling to Mars and so on, he is not taking no for an answer. And finally, also Richard Branson. I really hope that there will be millions of kids inspired to also go into space one day. I don't know whether millions of kids, whether that's a good idea, but at least the opportunities are created thanks to the visions of persons like those three. Absolutely. Okay, what is space? I think that's something to be left for after the break, and then we'll continue with that topic. Thanks for your patience for now. Okay, everybody, welcome back again. Again, apologies for the huge amount of material that I'm sharing with you today, but let's see how things go. Okay? Before the break, we had a look at a bit of history and also modern developments of spaceflight. Now let's go to something more essential. What is really remarkable, what is characteristic for space? What can we expect when we deal with space missions? The first observation, a very obvious one, is that we are in a vacuum. There is no atmosphere up there. I mean, we're talking about 100, 200, 500 kilometers up. There's no atmosphere up there. Here in the picture on the right, you may recognize the situation. This gives you altitude. At 0 altitude, we have like 10 to the power 24 number density, particles per cubic meter. If we are at an altitude of 100 kilometers, we already are down to something like 10 to the power 18. And space missions, you typically find them at 400, 500, whatever, and up, you are at 10 to the power 14. So it's not completely without molecules, atoms, whatever you have, but it is much, much less, something like 10 orders of magnitude less than what we have here on Earth. If there is no atmosphere, that's a direct consequence, we can also not use it in our engines, in our combustion engines, or whatever you would like to have. So that certainly is putting certain choices very simple. We need rocketry. Also, we cannot generate something like lift or drag. Lift might be very useful for performing certain missions, launching and also coming back to Earth. That is at high altitudes certainly not possible. We also see, because there is no atmosphere, that there is outgassing of material. Take this simple pointer. If I put it in a drawer or whatever, it will be like this for hundreds of years. The batteries run out, but that's the only thing. If you put something in space, that is a satellite or what, it will slowly resolve. It will disappear. The molecules, the atoms in there, because there's no external pressure, they will slowly disappear. So that is something to keep in mind when you design your own spacecrafts, and you have to choose, do I construct my satellite, do I construct it from aluminum, or from steel, or from copper, or from another material, whatever you have. That certainly is a challenge here. And it has in particular implications when it comes to lubrication. Also lubricants will disappear slowly. So if you have a solar panel that is to rotate more or less continuously, going in orbit around Earth, continuously doing this, at a certain moment, if the lubrication is gone, then you have a very, very serious problem. So no vacuum, that is certainly number one. The other one is that we are in a very special thermal environment, absolutely. First of all, we can make the observation, because there is no atmosphere, that there is no phenomenon like convection, right? Convection is what we have here on Earth. When you heat your house, you have a radiator and so on. There is an atmosphere, there is gravity that creates warm air going up and slowly spreading in your room and whatever we have. Well, if there is no atmosphere, something like that simply cannot take place. Also, there is no atmosphere in the sense that it can convey energy from one place to the other. The only mechanism that we have is to do it by means of radiation. So it makes your thermal calculations on the temperature of a vehicle or an instrument or what, it makes them kind of special, so to say. The source of energy that we like to use, of course, is the energy coming from the sun. It's coming our way for free, and you would be a fool not to use it. But then it depends very much on whether, I suppose you guys are the sun, whether I find my vehicle on the sunlit side of the Earth, receiving the energy that you are emitting, or whether I have my spacecraft at the backside in darkness, that is exposed to cold space only. And that makes, in a steady state situation, a major difference, because the temperatures can change between, say, 120 degrees at the sunlit side, you guys all emitting energy, you are the sun, emitting energy to our spacecrafts, and it can reach a temperature of minus 27 degrees Celsius when we are at the dark side of Earth. So you can imagine that creates quite a challenge for the proper design of a spacecraft. Be aware of that and make sure that your design is okay. Radiation, another element that we find in space very significantly. Here on the surface of Earth, we are sheltered, so to say, by the atmosphere. And the atmosphere, lucky for us, it has a number of what we call windows. That is the wavelengths where it is transparent. So we have it, for instance, here in the visible part of the spectrum. We can, I hope you can as well, with the naked eye, we can recognize that Mars has a reddish color. We can recognize other colors in space if it is emitting at that particular wavelength. We can recognize each other. When a plane comes over, we can recognize the colors and so on and so on. There's a second window here that is related to the radio spectrum, the radio part of the spectrum, and that can be used very nicely to communicate with spacecrafts around Earth or around Mars or whatever. So that is nice. What's also nice about the atmosphere is that it protects us. It stops, for instance, ultraviolet radiation and X-rays, Röntgen radiation, coming from external sources towards Earth. And we can congratulate each other on that. If it were not for this and being exposed to that radiation, it could have very bad effects to our bodies, to the cells that we are made up, and so on and so on. Now, when we talk about spaceflight, we are, of course, that will be clear, we are above the atmosphere. So, good thing, we have an unobstructed view of any radiation at any wavelength coming our way. That's good. That's why we fly a Hubble Space Telescope and so on at 800 kilometers altitude. On the other hand, we do have this ultraviolet radiation. We do have those X-rays, and they are also harmful for whatever we put there, living bodies or otherwise. You have to be aware of that, absolutely. And it will destroy, it will have a negative effect on your electronics, on your plastics and whatever you might want to have on board of your vehicle. A modern spacecraft is 50% electronics. If you're not aware about radiation, if you do not do anything about radiation hardening, as it's called, your mission might be dead and gone very quickly. This is the radiation as it comes in waves. We all understand what is meant there. Radiation also has another component, that is, say, the particle radiation coming in with very high energy levels. So we're talking about protons and electrons. They create, we're going to look at it in a couple of weeks from now, they create what is called the Van Allen belts. So we have regions around Earth, here in the red and in the gray, where we have large concentrations of particles, charged particles, highly energetic particles, and they will have a very bad effect on your vehicle. Gentlemen, please, if you want to have a conversation, thank you. They have a very bad, notorious effect on your spacecraft. So if you want to put your spacecraft in space, advice number 1, don't go into the Van Allen belts. Advice number 2, if you really have to, make sure that your satellite is protected against radiation and make sure that it can still survive for 10 or 15 years or whatever the duration of your mission is. Be aware of this phenomenon. As a consequence of the highly charged particles, we have something that you might already be very well familiar with. The northern light and the southern light can be observed around the poles, and if you're lucky, already here in Holland, that's related to the same thing. Another characteristic of spaceflight is that we are in a what we call weightless situation. Objects have no weight. Wait a second. What is meant with weight? Objects, of course, do have a mass. In principle, take any object, anything. You can count the number of molecules, the number of atoms, the number of I don't know what. Add it up and say, okay, this is like, I don't know, 500 grams, something like that. 200 grams probably, yeah? I have a certain a certain mass. I have a collection of atoms in my own body. So, yeah, the scale tells me every Saturday morning how heavy I am. In addition to having mass, my collection of molecules, which I always take with me, whether I'm standing here or maybe on board the space station, I also have a weight because, very simply, gravity is pulling on me. Gravity is pulling me down, and there's a reaction force that is keeping me in a stable situation. So I have a weight simply because of the fact that there is the floor here keeping me at this particular position. If I were to jump, I have a bad knee, I will not exaggerate. If I were to jump, oops, yes, I did it. If I were to jump, if you were to jump better than I can, you would be weightless for just a split second because there's no reaction force. What do we have in space? Do we have something firm as the ground here that I can feel a force, a reacting force against? No, we don't. So everything is falling and there is no weight for the astronauts, not for the space station itself, not for any satellite. We are in a weightless situation. But we do have the space station and astronauts, we still have our mass, of course. So be aware of that difference. What is the consequence for a spacecraft? It is in a continuous state of fall. Again, something that I will come back to hopefully tomorrow to explain the idea. It's very straightforward, but we'll see how that goes tomorrow. And finally, and that's good news, because we are in a weightless condition, you can easily deal with very big and very heavy spacecraft, take them on by a robotic arm, and drag them around and put them at any place that you would like to have them. On Earth, going about with a space station of 500 tons, well, that would be a crazy exercise. I think we all agree on that. In space, you are free to do so. I'm not saying without any effort, but much, much more easy than what we can do here on Earth itself. Okay, some example questions for you to consider. If you think, well, I do not understand or whatever, feel free to send me a mail or ask the question on Brightspace. That's maybe even better. But try your luck with any of those questions. And then finally, the current trends. In the 1990s or late 80s, we had the big satellites. Again, nowadays we come to realize that they are extremely vulnerable for impacts by space debris. So that has been to some extent followed up by the CubeSats. And at this moment, we are working on even smaller spacecraft, the Pocket Cubes, that are also in development here at this faculty by students who are now in their second master year. Okay, I'd like to leave it to this for this first part. Now let's see if I can do the trick again. My dear friend, the TA said, first push escape. It works. Thank you, my dear TA. Okay, I'd like to continue the coming half hour, slightly less, hopefully, with the discussion on launchers, one of the prime elements that we find in spaceflight. Questions: how do we get in space? Developments, some examples of launch vehicles, and some typical profiles that you might encounter. But first of all, back to basics. Why launchers in the first place? Why rockets in the first place? Can't we do it in a different way? The first bullet already gives you one of the prime answers there. I made observation just a moment ago that there is no atmosphere, no air. So anything that we might use here on the surface of Earth, or say at an altitude of 10 kilometers, your jet airliner, whatever you have, that by definition will not work in space. We have to come up with a different solution, absolutely. The second observation, I'm not going to jump up again, but you understand it. We have something standing on a launch platform at Kennedy or Kourou or Baikonur or I don't know where, and it has to be put in space. Well, the story about weight, mass and weight, that also applies for a launch vehicle, including the spacecraft on top of it. There has to be a force that fights against gravity and puts up to a higher altitude until we finally reach the destination, let's say 800 kilometers. So you have to fight against gravity, as I said here, to provide the brute force. It takes a big force, a really big force, to put your Saturn V or whatever you have into space. Really, you need enormous engines. Some of you have observed it in Kennedy, at Kennedy Space Center. You need enormous engines to provide this force to have your vehicle taken off into the air, in the end, into space. And then finally, we have to reach a certain amount of energy, potential energy. We have to reach an altitude of 800 kilometers, but we are not interested in a ballistic flight. Once there, we don't want to fall back to Earth again. We want to be in a sustained flight, something that goes about the Earth continuously, and therefore we also need a certain amount of kinetic energy. And we'll see the numbers coming up tomorrow. That is 7-point-something kilometers per second. So a very high velocity indeed, something like 28,000 kilometers per hour. So for all of that, to achieve all of that, you need a very, very powerful mechanism, and that is your rocket engine. You see here an illustration, Friendship 7, one of the very first US launches. You might recognize it, I don't know, here on the top, there's a small capsule, the Mercury capsule, and that contained John Glenn, the very first US person to be in orbit around Earth. Well, a large amount of energy was needed to put him in that particular situation. Actually, the guy was completely crazy. He was sitting in this small capsule. It was something like 1.5 meters by 1.5 meters. And he was in this chair and had to hope and pray that everything went okay. He was all crazy because, let's put it very mildly, way back then, rockets, we did not really understand them that well. They had this tendency to blow up. Any volunteers? We had some volunteers way back then. Nowadays, of course, it would be unacceptable if 1 out of 2 blows up. But way back then, people were not asking questions, I don't know. They simply did what thought needed to be done. John Glenn, he later became senator, so he was not so stupid at all. And very, very late in his life, he became a passenger with the space shuttle to visit the space station again. So he did have quite a number of remarkable events in his lifetime. Okay, what kind of types of propulsion can you think of when it comes to designing or selecting, or I don't know what, a rocket vehicle? The most straightforward one is what you see depicted here in the green, this one. That would be what we call a solid propellant rocket engine. You might recognize the green indeed. It says here propellant grain. It is a solid thing. It's not fluid, it's not gaseous or whatever. If you provide enough heat, why is it stopping? Oops, sorry. If you provide enough heat, energy, it will ignite by itself, generate hot gases, gases with a lot of pressure, and they are then expanded here through the nozzle and create momentum in order to generate your thrust force. So that is the most easy thing. In addition, as an alternative, you can have what we call a liquid rocket engine. You see a picture of that here on the left. We have a fuel and an oxygen. The fuel is burnt with the oxidizer. Together they are the propellants. And just follow the lines, as everybody would do. The oxygen is going like this, and then going into the combustor. The same story goes for the fuel. It's going around like this into the combustor. There, the two of them, they mix and they burn up, create this hot gas under a lot of pressure, and that is then expanded through the nozzle. So that is clearly a quite different concept. Why consider two concepts? What will be the pros and cons of each of them? What do you guys think? Let's first here have some hands on the solid rocket engine. What will be an advantage or a disadvantage of that one? The answer is it's probably cheaper. Yes, there's not so many components, so yes, it is cheaper. Anything else in favor or against the solid rocket engine? The guy in the back. It has less volume. You do not need the big tanks. Well, you need a storage, something for the solid material, but there's a good chance indeed that it might be smaller in size. Yes. The neighbor, you had your hand up there already. Controllability, a disadvantage, indeed. Once started, you cannot turn it off anymore. It has to burn completely empty. So yes, the total performance, the total delta V is a given. You cannot do anything about that. Whereas for the liquid one, of course, you have valves. You can open the valves, you can shut the valves, so it's in a much better controlled situation. Anything else? I hear quite a number of good answers here. Yes? You can launch it faster. Why is that? If it's liquid, you need to prepare it. Yes, you're right. If it's liquid, you need to load the tanks. In many cases, we have liquid propellants under a certain condition, cryogenic. That is at very, very low temperatures. So you can only do that very, very shortly before the launch itself. Your solid rocket option is in principle ready to go at any moment in time. Your solid rocket propulsion technique is something that you can find in weapons, because you just have to push the button and there it goes. But yes, you have a good answer. Anyone else? Maybe they can provide a higher force in a shorter amount of time. That's a matter of tuning the parameters of either the solid propellant one or the liquid propellant one. You can play around with that and, in principle, get a certain amount of force at the level that you like. The very last one, I want to continue.
Liquid ones have higher specific impulse, so it's more efficient.
Yeah, someone who has been reading the books already. Very good, or not, using your imagination, I don't know. The liquid, no, but the answer is good. The liquid rocket engines typically have what's called a higher specific impulse. You are curious now, what on earth is that? Again, it will be on the table 2 weeks from now, but it means that the liquid propellant technique is much more efficient when it comes to dealing with 1 kilogram of propellant compared to the solid ones. In summary, we have advantages and disadvantages to each of the two. And when it comes to you guys making a choice, you should be aware of those pros and cons and make the proper choice. Of course, we can think of mixtures. We can have them in a hybrid mode, where the fuel, for instance, is a solid and the oxidizer is still a liquid. That's all possible. We can also have nuclear rocket engines. And please don't think that that is something that is on the table only now or since a couple of years. The Americans were already working on that in the late 60s, in tests in Nevada and I don't know where. We can also think about, electromagnetic propulsion, ion propulsion. Very, very small levels of thrust, but extremely efficient. Back to your remark, how do you call it? What you get for your investment in terms of kilograms for an ion engine, that is maybe a factor 10 or 20 or 100 better than what you can get for any of the other techniques. So when mass is of importance, and it's typically like that in spaceflight, an ion engine certainly is something to consider. And then finally also solar sailing, using the pressure from the photons from the sun, using that as a propulsive means, that also is one of the options that you might want to consider. Okay, how does it work, a rocket? In essence, it's based on conservation of momentum. We are going to do quite extensive treatment in a couple of weeks from now, but for now, let's say action is reaction. Action is coming from one source. Reaction is what we would like to have. Action is coming from the rocket engine that burns up hot gases and throws them out, expels them with very high velocity. So that generates certain thrust, and the thrust is equal to the product of the mass flow times the exhaust velocity. Please accept my words just for now. We're going to derive all of that in a couple of weeks from now. So that creates the thrust. And if the thrust is put on a certain vehicle, of course, as reaction, we get an acceleration of that vehicle. F is m times a, and we can readily do the calculations there. Instantaneous mass, of course, times instantaneous acceleration. The trick is to get the proper amount of thrust needed for your particular objective, whether that is launching off at Kennedy or doing a certain maneuver in space to end up in another orbit. All of that is something that can be part of your problem. Okay, Tsiolkovsky, you saw the name appearing before the break. Again, we're going to derive his famous equation as well. You see it here, the end velocity that can be reached by burning up a certain amount of propellant is proportional to the ratio of those masses times the exhaust velocity, the velocity with which the atoms or whatever are thrown out. Again, we're going to derive all of it in a next lecture. Okay, an example. What can we use to illustrate the principle of this? This, of course, is a very bad example. It's the V2, the German Vergeltungswaffen, right? It was launched from Wassenaar and supposed to reach the city of London when we had World War II ongoing. But on the other hand, let's be very neutral here. It can also be used as a nice illustration because it's very elementary, a nice illustration of the concept of rocketry. So what do we have here in this rocket? First of all, we have an oxygen here, the oxidizer in this tank. We have the fuel in the upper tank. In this case, it was clearly alcohol. The two of them, by using pumps, were fed into a combustion chamber, as we see it here, and then expelled through the nozzle with high velocity to generate a certain force, the thrust force. You see, of course, that the rocket has a certain aerodynamic shape. When launched, it has to work its way through the atmosphere, and you want to have the aerodynamic losses as small as possible. So clearly that is taking place here. The warhead is at the very top. The warhead is not a nice application, of course, but nowadays we put the payload there, payload as in a satellite that needs to be taken somewhere or whatever. There's a number of aspects that were very, very novel when it came to this particular design. The first time around that we had a rocket like this. For instance, we have a number of vanes. You see 4 of them externally, 1, 2, and there are 2 others, 4 big vanes to control the vehicle. It is supposed to go up, and it's like steering it by playing around like this. But we also have a number of vanes internal that might deflect the flow of material coming out internally. So that was something that is related to attitude control in order to fly to your destination. Completely novel way back then. And also you might observe here a word that says control compartment. Nowadays, we would call it avionics. That was completely non-existing way back then. It was all invented during the Second World War and applied for this particular piece of machinery. Again, apologies. It was a very, very bad tool for anyone involved, but it forms the basis of what we are doing still at this very moment. And in terms of size, you might recognize this gentleman here with the funny trousers. It measures something, what is it? Well, if this is like 2 meters, it measures probably something like 25 or 30 meters in height. That's the kind of thing that we are talking about. Okay, some questions, and you could easily do the exercise. I might have questions like this when it comes to the examination. What, for instance, is the mass flow? Mass flow as in kilograms per second going through. Well, the previous sheet said it has a lift of mass of 12,800 kilograms, propellants 8,800 kilograms, and apparently it's burned up in 68 seconds. So, my dear friends, we end up at a mass flow of about 130 kilograms per second. Mind you, we're talking about the elementary space flight. That is 13 buckets of water each second, and that 68 seconds in a row. Do not underestimate the technical challenge of coming up with a piece of machinery that is doing this. What is the exhaust velocity? Well, I gave it away already 2 sheets ago. Thrust is equal to the product of mass flow times exhaust velocity. We know the thrust, right? That was here, thrust, 250 kilonewtons. We just calculated the mass flow, so you can really come up with a value for the exhaust velocity, almost 2 kilometers per second. And believe me again, that is a very, very impressive number. One of you came up to me in the break, hey, how about there? What can I do there? Would I be allowed? And so on and so on. The dare guys probably are jealous when it comes to a number like this. And finally, what is the end velocity? Once all the propellants have been burned up, with what velocity do I find my vehicle, ignoring drag losses or whatever? You can do the exercise using Tsiolkovsky's equation, and you end up at something like 8,000 kilometers per hour. Quite something. A wonderful, apart from the application, again, don't get me wrong, let's not make any sick jokes about that, but a wonderful piece of machinery, absolutely. Okay, I'm going to challenge myself again, but I hope I know the trick by now. Let's see. Escape was the buzzword. Somehow I should be able to turn it off, but okay. Skip ahead. There we are. Again, apologies for the noise being absent. But this is one of those V2s. It's tested at Peenemünde, which was the test site for the Germans, somewhere in the Baltic Sea. And you can see it lifting off. And again, this is all very, very experimental, so very impressive indeed. There's some beautiful sound to the movie, but again, pick it up this evening and play it for yourself. It's not always going okay. This one apparently is. Trouble develops, use your imagination. Starts to rotate in another direction, Whoa, it's not designed to survive that. The person here, that's von Braun, this one. Trying to look away. I didn't have anything to do with this. He did. An ill-fated rocket. This is a beauty. Up, 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 up. No, let's come back. Close, but no cigar, I guess. Nine tons of propellant. Don't think too easily about this. It was quite an experiment. Sorry guys, spoiling your day. Okay, there's plenty of movies to be found on the internet, so please enjoy and see how difficult it was way back then. Sure, question. You're not sure what the difference is between end velocity and exhaust velocity. Yeah. Okay, very simply, if this were my rocket and I throw out the propellants burned up in the combustion chamber, I throw them out with a certain velocity. That is what's called exhaust velocity. And then my vehicle is accelerated. Let's say it starts with velocity 0, but because of the thrust, it accelerates and accelerates and accelerates until everything is burned up. And then I have my end velocity. Yeah? You will never ever forget, right? I skip this one in the coming exam then, if it's okay with you. Yeah? Hey, one thing more that I want to say about the V2. Again, it was the very first real rocket. And at the end of the war, of course, there was quite a bit of interest, both from the Russians and the Americans. The Americans were more than happy to capture, so to say, Wernher von Braun, transport him to the US, punish him a little bit, never do that again, and now you come to work for us, right? Yeah, really, that's what happened. So if you look at all the vehicles, all the launchers that have been flying in the US space program, almost all of them are a straight derivative from the V2. The role of the V2 cannot be underestimated. Certainly not. Okay, we spoke about all of this already. Again, the sequence, the layout of a liquid rocket engine. Again, fuel coming in, and that is used to, well, for instance, also to drive the engines, to start the engine, and drive the turbo pumps that will pump the fuel and the oxidizer. The fuel can also be used to cool the rocket nozzle. That can be something that is extremely hot. In this case, it's what's called regenerative cooling. So the fuel used for cooling is fed back into the combustion chamber. As an alternative, you can also dump the fuel that's used for cooling and then simply not benefit from that at all. The design is a little bit more simple than what we have here on the table, but again, you as a designer have options for that as well. An example, again, going back to the guy who was at Kennedy and some others, you might have seen something like this. Look at this. This is the first stage of the Saturn rocket. You might recognize a certain person standing here, and it is really a beast of a piece of machinery. 42 meters high, sorry. 42 kilometers high. That's only the first stage. The total thing will measure something like 110 meters, and it is huge in terms of size, huge in terms of mass, more than 2 million kilograms, huge in amount of thrust, 33 million newtons. It needs that force to lift off from the launch platform. That's quite obvious. What do we also find in principle, any launch vehicle? That is what is called the payload fairing or the shroud. You can see it here while still on Earth. It is covering the payload, the satellite that is to be put in space. And here it is being thrown off once we are at a certain altitude. And the reason for having a shroud is very simple. It needs to protect the payload from heating, from other things. You find them here on this sheet. But once we are above the atmosphere, it doesn't serve a purpose anymore. We don't want to accelerate any dead mass, dead body, so we throw it off and we continue the mission without this particular shroud. A very, very common thing to do. At the very end of the day, once you reach your altitude, you also need to give it the proper velocity. So in many cases, we might decide to go to what is called an upper stage or a kick stage to give you an extra delta V of something like 1 or 2 or 3 kilometers per second. You can recognize, you can recognize a person here for scale. Some of them are indeed very, very large, but we also have the smaller ones as you find them here or there or what. So kick stages is something that you encounter quite regularly in real space missions. Some examples of US launchers, and I just want to point out only one or two. The SpaceX, the Falcon 9, you see it here, and the Falcon 9 Heavy, that's this one. They, of course, pale compared to the Saturn V over here. Also, the thing that is in development at this moment, the Space Launch System, it might be in the news in the coming months very regularly. They plan to do a test flight with that, but I will try to keep you up to speed. Russians have the same collection of material. A nice example in this one. Do you allow me to take another 3 or 4 minutes? Yeah? This is a beautiful collection of pictures, if only because it shows you that the Russians use rather, say, traditional ways to transport their launcher to the launch pad. As the English are saying, if it ain't broken, don't fix it. The Soyuz has flown like, I don't know, 1,500 or 2,000 times, almost always with great success, so this technique works. Why make any change to that? They also had their Buran. If you think it looks a little bit like the space shuttle, you could be right. I have no idea why. And finally, this one, the Buran, by the way, flew only once or twice. And this is the famous, the N1, the Russian moon rocket. As said, in the late 60s, the US was in competition with the Russians to be the first to put astronauts on the moon. So the Russians, of course, in principle, they had all the technology. They designed their N1 launch vehicle. Unfortunately, an element, or an interesting element, was that they had quite a number of rocket engines here at the bottom end. And they had to be synchronized, of course. You have all of them ready to go at the same level of thrust, and so on and so on. And that was one step too far. So in the end, there were 4 launch attempts for the N1, and all of them failed. Sadly, it would have been very interesting if it was successful, but this is, also another part of history. Europe, at this moment, Ariane 5 is our workhorse. We are developing the Ariane 6. We also fly Soyuz vehicles. Don't be surprised. This indeed is a Russian vehicle, but we fly it from Kourou. Very nice because it is close to the equator. The number of spacecraft launched, you can see a high here when it comes to Russian military. Why would that be? Why do we have a big bump, a big high of Russian military spacecraft, say, in the range from 1970 until 1990? Yes, the Cold War was still ongoing, yes. And then, the Americans were in the same Cold War, right? Well, US military that is blue, this blue, they only launch, well, say a tenth or less than a tenth of what our dear friends the Russians did. Well, dear friends, until 3 days ago. How come? Why do the Americans do a certain job espionage. With a limited number of vehicles put in space, and why do the Russians need a 10 or 12 or 15-fold of that? And 9 out of 10 failed. It's not exactly like that. But you say the Americans are better. Yes, they were better, or they are better from a certain perspective. As I said, what was the purpose of all those missions? Let's be honest, espionage, right? So the Americans, they are overflying Moscow, let's keep it simple, and they have their cameras developed by companies like Kodak and what do you have, and they were great instruments. So from an altitude of say 400 kilometers, they could observe something in the backyard of Brezhnev or Khrushchev or whatever we have with a precision resolution of say 2.5 centimeters. Perfect cameras. The Russians, they also had their cameras, but they were not so good. They could only observe things with a level of detail of say 10 centimeters at the same altitude. But they still would like to see in the backyard of the White House what is going there, the Pentagon. So if your resolution is like this, and you're stuck to that particular piece of instrumentation, what options do you have to get a better resolution? Get closer by. Do not observe it from 400 kilometers, where's the White House? Here. Not from 400 kilometers, but from 200 kilometers. And then you have a similar resolution. You can do business. But at 200 kilometers, we have quite a bit of drag. Your spacecraft will burn up or be forced to burn up in the atmosphere within a week. So yes, there's only one remedy against that. That is fly a new mission every week. The Russians had to do it every week, and the Americans were good enough with, say, 2 launches per year, something like that. So that's exactly the reason for this. Okay, very quickly. Launches are not perfect. There's a certain success rate. The performance very much depends on the altitudes that you want to fly at. Overview of launch site, you believe that. Stages. Typically, when it comes to launching from a launch site, you will be confined in the direction in which you can launch. You don't want to have your first stage or whatever land on Earth. So that has limitations then to the inclination that you can achieve. This is very good. Very good. Ariane 5, very successful mission. And new commercial rockets, let me show you just one. The track record of Falcon 9. Falcon 9, we thought, before New Space came around, we thought Ariane 4, Ariane 5, Ariane 6, they would do great for many centuries to come. And then our dear friend Elon Musk came along and said, well, I have different ideas about designing a launcher, building it, flying it. I think I can do it much cheaper. Actually, about 1/3 of the price that we had to pay for an Ariane. Consequence of that, you see it here. They have up to something like 26, 27 launches per year. They captured like 80% of the market. A great commercial success. A company like Boeing cannot sit back and do nothing. They will be blown out of the water. Absolutely. So kudos to this. Please check out whatever you can find on the internet on this. But it's a great activity. Thanks for your patience. Sorry for taking a little bit longer, but I hope to see you